Hi, friends. I'm Maddie. Welcome to Science Side Up. And this is yet another episode of Journal Club, where we read and kind of live critique. So this is unedited, unscripted. I'm learning things with you guys. Young Earth creationism research articles, and I put those big quotes because they do not meet the standards of actual scientific articles, even a little bit. And so yeah, anyway, that's what we're doing. Why are we doing it right this second? Guys, I just turned in to my advisor a copy of a chapter. I just turned in a chapter of my dissertation to my advisor for him to edit part. And instead of going inside and throwing up from anxiety, I figured I would maybe chat with you guys and read something that reminds me that I do in fact know something about science, and I'm not a complete idiot. Which is how I feel a little bit as I write a dissertation. And should I have just said I submitted my first chapter to my advisor? Yes, except in my brain, I'm like, but I didn't submit chapter 1 to my advisor. Because chapter 1 is the intro and lit review, and that I've got to finish. That still has to be edited. And then chapter 2 is methods, and chapter 3 is this big section of results, and then chapter 4 is this other big section of results. And chapter 5 is a third big section of results. And then chapter 6 is the brief summary of so what. And so I actually turned into my advisor chapter 4 because that's the one that is done, and nothing else is. And I'm defending in 2 months. And hey, let's not talk about that anymore. It's going to be great. My space is dark. I'm working on this is where I've been working a lot, and I've been needing it to be cozier because of the aforementioned overwhelming sense of doom associated with the last 2 months of your PhD program. And so you can't even see it, but I got little twinkle lights back here, and they're actually attached to leaves and vines. But I normally actually have a big studio light that's blaring right in my face. This light is coming from a ring light that's a little dimmer and more it's not quite so blinding and hot. And that's just that's also why I have my comfort leaning on, right? And I just heated up my coffee. So we're working on I got to be a little cozier right now because of, once again, the aforementioned sense of doom. But hey, enough about my existential crises. How are you guys? Let me know. Hopefully we're chatting in the live chat now for a premiere. But yeah, okay, so we're gonna keep on this weird, just hubris dipped part 1 of about Milankovitch cycles. And I got real mad about it in the last journal club, and I don't know if I ranted and raved, if my ravings in the last video were coherent. But this is part 1 of a 3-part series about should this super iconic paper, pacemaker of the ice ages that originally proposed Milankovitch cycles, which are orbital cycles that cause periodic glaciation, here down on planet Earth, good old terra firma. And as we learned last time in this introduction, that if our author that I've been referring to is J.K. If J.K. understood how seasons worked, then he would understand the concept of Milankovitch cycles and glaciation, right? Periods of glaciation. And that made me real big mad when I was reading this. And then also I wanted to point out that if you propose a theory in scientific literature, right, and it passes peer review and your work is good, right, you don't retract that if it's later proven wrong, right? We leave our bad ideas, right? We leave what we thought were good ideas at the time but turns out wrong in the body of work, right? to provide a like complete record. So the only reason you would retract a paper would be like if you committed academic fraud in some way, right? Like if you stole research, or like your methodology was so bad, right, that it was like, that would be a reason to retract a paper, not I proposed a theory and 30 years later it was proven wrong. So like even this idea of even if Milankovitch cycles and climate change weren't Milankovitch cycles as a cause of natural climate change, right? Even if that wasn't real, which it very much is, that still wouldn't be a reason to retract a paper, right? So like the premise here is silly and not how science works, and Jakey Poo should understand that. He is a scientist, right, or engaged in real scientific discussion and work. So yeah, some bad stuff right off the top. Read this. We talked about last time how power spectrum work. That's a great analysis tool. And so we're not going to get into what an oxygen isotope ratio is. I'm not a chemist, and we kind of talked about that a couple journal clubs ago. So we're going to skip reading this bit because this is just like okay. So let's start here with marine isotope stages. And so now we're back to stuff I haven't read yet. Anyway, okay. So as previously noted, if one plots oxygen isotope values from a sediment core as a function of depth, you'll observe many wiggles, a very scientific term there, wiggles, with occasional prominent peaks and troughs. Okay, so it's not constant over time, right? There's interannual variability of oxygen isotope ratios as a function of depth, which we can take as an analog for time. Cool. In fact, this is also true for other quantities that could be measured within the core, as estimated sea surface temperatures. Amazing. Yes, absolutely true. If we take depth as an analog for time and oxygen isotope values as an analog for temperature, then we can create a temperature versus time plot that shows temperature varies over time. And he's saying that all of that with the word wiggle there. Cool. Relatively high and low, forum, FORAM. Yeah, that sounds like a biology term. I'm not a biology or paleontology term I'm not super familiar with, but that's okay. So this is looking at colder and warmer climates for different values of those oxygen 18 ratios. Cool. More precisely, the highest values of oxygen 18 within a sediment core are thought to indicate times of maximum glacial extent. We've read about this, how oxygen 18 ratios are also related to global ice volume. So not only could we pull out a temperature analog, we can also pull out global average ice volume from these values. And the smallest values of the oxygen 18 ratio are thought minimum glacial extent. Cool. Yeah. So we could also make a plot out of this data, right, for global ice volume, or so that's like glacial, the total amount of area on planet Earth covered by glaciers, covered by ice, or permanent ice. We could do that. We could make that graph so of like area covered versus time. We could pull that out of this oxygen 18 data. Obviously, there's going to be error bars within that, all that jazz, right? But you know, this is a paleoclimate tool. Because uniformitarianism, wahaha, paleoclimatologists believe that changes in this oxygen 18 values are indicative of global climate variations. They have devised a numbering system to identify prominent features in the oxygen 18 signal, which should, in principle, be present in every sediment core, assuming, yeah, so this is the idea here. I love this, like, uniform, this, like, he's being all sassy. This reads very sassy to me. Uniformitarian, one, that is a in modern times a uniquely creationist term. So they're just trying to avoid saying scientists, right? Like you don't have to say paleoclimatologists. So non-young earth creationist paleoclimatologist, please name me a paleoclimatologist who works in that field, who is a young earth creationist, right? And who's like science is affected by that belief, right? So this is we could just get rid of that adjective, right? Uniformitarian adjective. And we could just say paleoclimatologists. And it's not believe, right? It's they have evidence to support, right? Because so let's read this again as it should be written. Because paleoclimatologists have demonstrated that changes a mechanism by which oxygen 18 fraction changes is correlated with global climate variations, right? That's how that should be read. So we have a numbering system to identify prominent features. Cool. Yeah. So like, hey, I dug up this core in the Indian Ocean, then I dug up this core in the Atlantic Ocean. How do I match up the times? We're going to look for specific peaks. This is kind of the same idea as like looking for that like iridium layer in geologic columns and being like, ooh, okay, so we have this one global iridium and we know that this happens at the same time worldwide, right? So now I can match up these two rock formations and know when this formed, that this was forming in China at the same time this was forming in South America or whatever have you, right? Like we've got to be able to like relate our data across space, and looking for like global features is a useful thing. So, cool. Secular, again, you can just say paleoclimatologists use a numbering system called marine isotope stages, or MIS, to identify the alternating warm and cold periods that they believe are indicated by the wiggles. Again, that's really condescending, right? And it's sassy. The sass here is just absurd. Just to describe, like, please go to your like high school or middle school math class and look at a plot and describe it as like, well, the line wiggles. That's your analysis of it, right? Cool. So this is how that numbering system works. I'm not super... Boundaries between the stages are usually placed, okay, yeah, at the midpoint between the minima and maxima. Not presumed, right? This is saying presumed minima and maxima, right? And presumed would mean assumed without support, right? That's not what we're doing here. We're not assuming this to be true without any reason to do so, or without like data to back up why that's a good assumption, right? For example, here's a good assumption for a physics problem. If you're doing like a mechanics problem, block is sliding down a ramp, you don't need to take into account, the difference in gravity, the difference in the force of gravity between the top of a 1 meter ramp and the bottom of a 1 meter ramp, right? We could say, hey, we're just going to assume for the sake of this problem that gravity on a near Earth's surface is a constant, right? Because in the grand scheme of things, the difference in the gravitational force, if you were to actually calculate it out between like at Earth's surface and 1 meter above Earth's surface, right, is negligible, right? It's not... it would be, within the rounding error of your of where you're like, if you round off to 3 decimal places, then the difference caused by that difference in force is going to be below where you rounded, right? So that's kind of what that's like an easy example of that's not a bad assumption, right? And so like the assumption but that, hey, this data that we're plotting, these paleoclimate temperature analogs, is in fact, we're plotting temperature now, and it's got error bars, right? And it's not perfect, but it's good, right? Something doesn't have to be perfect to be useful in science. And so this presumed minima, maxima, no, it's not presumed, right? It's we have, right, there's a lot of science and like just straight up math and basic chemistry behind why these things are true, right? It's not just made up. It didn't just come out of somebody's head, right? It's tested in a lab, where it can be, and there's like known mechanisms, right? Uh, this isn't presumed. Okay. The approximate locations of the, we don't need this word, marine isotope boundaries for the core in the Shackleton paper. I keep saying Shackleton paper because that's the author I recognize, but he's the third author on it. The Hayes, Embry, and Shackleton paper. Yeah, so they plot, he's noticing that there's like inverted scale, so it's because there's an inverse relationship between temperature and oxygen 18 ratios, and so we're going to plot this so that if you go up, that means warmer temperatures. If you go down, that means cooler temperatures. So your oxygen 18 axes are flipped. Okay, cool. That's just an explanation, albeit a sassy one. Okay, the termination to causality problem. I'm excited for this. A termination within an ice or sediment core is defined to be the oxygen isotope ratio that represents the midpoint between full glacial and full interglacial periods. Cool. Love that we have a citation. As we have already seen, these terminations generally mark the boundaries between marine isotope stages. Cool. Termination 2 is the name given to the end of the penultimate, second to last, glacial interval, thought to have occurred roughly 130,000 years ago. Although one might expect from figure 2 that the penultimate glacial interval would correspond to MIS 4. Is this his figure 2? Where's figure 2? Here we go, figure 2. So where is depth? So this would be maybe here. Is this what we're talking about? This point, I think, or this one of these two. So he's referencing this figure. Let's go back to what he's writing about. And so I think this is it because like depth, as depth goes up, time is going further back. So like depth of 0, this would be time now here. This would be time now, and then so this point here should, yeah, warmer temperatures now. So this should mark the end of the last glacial maximum happening here. Okay, cool. In theory, if I'm reading this correctly. Okay. And now he's trying to say, though, one might think, no. One might expect from figure 2 that the penultimate glacial period would correspond to MIS 4. Okay. Regular paleoclimatologists consider MIS 2 through 4 to be a single glacial interval, according to Wolf et al. 2010. Wait. Glacial interval, although second to last. Oh, I see. Okay. So corresponds to the MIS 6.5 back. Okay, so this is saying oh, okay, yeah, this is saying that like this region here is a single period of glaciation. And so this between 5 and 6. I mean, yeah, that kind of makes sense. The trend from here to here is down. We have a downward trend from here to here. And arguably an upward trend, right, all over here. Anyway, so okay, sorry, I was reading this stuff. So you're saying that this point here is the 130,000 years ago. The second to last, the end of not the last ice age, but the ice age before it. Cool. Okay, why are we mad about this? The manner in which terminations have been defined. Cool. The causality problem refers to the fact that some data sets seem to imply the transition from 6 to 5 occurred 103 to 145,000 years ago, even though the increases in high latitude sunlight that supposedly caused the transition should have occurred approximately 130,000 years ago, according to approximately, that's fun, Milankovitch expectations. In other words, the effect appears to precede the cause by multiple thousands of years, an obvious problem for the Milankovitch hypothesis. So here's the problem with this, right? Approximately 30,000 years ago could be 145,000 years ago, right? Approximately 130,000 years ago could very well be 133,000 years ago. So like, I would need, so the problem here is what he's trying to say is that if the Milankovitch cycle, right, the part of the Milankovitch cycle that was going to cause this interglacial that started, right, if we transitioned in a Milankovitch cycle in our orbital mechanics sense to a orbital cycle that favors glaciation, if that transition happened at 130,000 years ago, but the change in the interglacial, the change in the temperature data happened between 133 and 145,000 years ago, then therefore the change in temperature, right, preceded the orbital change, right? That's what he's saying. Here's the problem with that. The error bars on the Milankovitch cycle, that's not shown, right? So the error bars on the Milankovitch cycle isn't shown here. And so like he only gives this approximate, hey, this should have happened 130,000 years ago, but this happened 133,000 years ago. Causality problem. That's not, no, like that's not, if that were true, that would be a causality, that could be a causality problem, right? We could, right? So that would be interesting. However, he has not demonstrated that to be true because those error bars matter. So you can't just say approximately 130,000 years ago and then follow that with aha, right? Because I don't know what the error bars, I don't know what that approximately 130,000 years ago means, right? And also the Milankovitch cycles, right? This is a thing that's constantly changing. The eccentricity of Earth's orbit is constantly changing, albeit very slowly, with a periodicity of about 100,000 years. So what that means is that, like, if we were to go from now and then we were to compare Earth's orbit now and Earth's orbit 100,000 years ago, they should be the same. But Earth's orbit now and Earth's orbit 50,000 years ago should be different, right? But it's a constant change between those things. So, anyway, so he hasn't actually presented a problem, right? Or the problem he is hinting at, like hint, hint, nudge, nudge, is not presented with sufficient data, right? There's not sufficient information to draw the conclusion that he's making. So this is like bad, if this was the chapter I'd submitted to my advisor today, this whole section would just be a red pen, right? Like fix it. With that probably fix it, because this is bad. This is undergraduate level bad, right? I mean, I'd probably give it to a high school student. I would tell them to, like, hey, be more specific. Can you find some error bars on that? Right. But if it was an undergrad, like if it was a high school student, I would explain to them what they did wrong. If it was an undergrad, I'd be like, do better. And hopefully they would know what that meant. I mean, in reality, I'd probably explain it to anybody who made this mistake, but like, I hope it would be condescending to an undergrad. That sounds so bad. Oh no. But you know what I mean? Like I don't expect a high school student to know better. I would expect an undergraduate student to know better, right? Right. Okay, so let's go on to orbital tuning, shall we? Okay, because most seafloor sediments contain low amounts of heavy radioactive elements, radioice. This is not right. Jeez. Okay. Jesus, hold on. The sentence is bonkers. Let me get a sip of coffee while it's still hot. Hey, team. Seafloor sediments. Yeah? Do we date sedimentary rock with isotope dating? We don't. And why is that? Why do we not date sedimentary rock via radiometric dating? Because we would be dating the individual pieces, not the age of the rock. That is okay. So you cannot radiometrically date. That is confusing the age of the wood in a house, right? Or the age of the stone. Age of the stone. Let's say you built a house out of rock, right? And you are the third little pig who the big bad wolf could not blow his house down, right? So you built your house out of stone. Is that a... No, sorry. I'm thinking of a children's song from Vacation Bible School about not building your house upon the sand, and that's going to play in my head all day now. Cool. Great. Thank you. Yeah, so if you built your house out of rock, right, and we wanted to know how old is the house, if we were to radiometrically date the rock, right, we would get the age of the rock. And that would tell us, oh my gosh, this house is 70 million years old. Whoa. Obviously, that's very silly if you know you built your house last week, right? Therefore, there are certain times when radiometric dating is the inappropriate tool, right? That's the inappropriate tool to figure out how old something is. In the sense of, and that also wouldn't tell us that age. If we were to date the rocks, that wouldn't tell us, hey, when were these rocks taken out of the quarry, right? Can't tell us that. It can only tell us how old, how long ago did this rock form. Okay, so sedimentary rocks are made by a big rock getting ground down into like sand, right, or smaller pieces, but basically sand. And then that sand mixes with other stuff. And then that sand mixes with sand made from other types of rocks and dirt and stuff, right? And then all of that big mixing pot sand soup gets pressed together with heat and pressure, right? And over a long period of time, fuses and becomes sedimentary rock sandstone, right? Stuff like that. And so each piece, each little itty bitty individual grain of sand that is in that sandstone or that other type of sedimentary rock, right? If we date that, that is dating the rocks you use to build your house, not the age of the house, right? So we would be dating the age of the rock that got ground up to make the sedimentary rock, not the age of the sedimentary rock. So we can't use radiometric dating to date sedimentary rocks. Now, if you had like a piece of like coral or seashell, right, that was intact, and you wanted to know when that seashell was made, you could. I don't. A seashell is the first thing that came to my mind because we've been talking about like shells and calcium carbonate. You could maybe date that. I don't know of the method. Right, because you couldn't use carbon dating because you can't use carbon dating, gives inaccurate results for marine sediments, right, for marine life. And so like that's the wrong thing. And I don't know enough about the types of radiometric dating that I'm familiar with are uranium lead dating, argon dating, and carbon-14, right? Those are the ones I know stuff about. So like if you're trying to date something else specific, and again, not the age of the sediment, but the age of the things in the sediment, there's maybe a method to do that, and he's kind of referencing that. But just right, like use the right tool for the right job. So let's see what J.K. Poo is saying here. Here we go. Because most seafloor sediments contain low amounts of heavy. So again, it's the wrong reason. Radioisotope. So we don't directly date seafloor sediment with radiometric dating for common sense reasons, because we don't want to apply the wrong tool to the job. Cool. I don't know about this protractium thorium dating. I don't know anything about that. So let's leave that alone. So, oh my gosh, relatively young sediments, with ages. So sorry, radiometric dating methods cannot generally be used to directly date the seafloor sediments with ages beyond the range of radiocarbon dating. And if you're doing radiocarbon dating, you have to be super careful because of the phenomenon of old carbon getting used. So the ocean is a carbon sink. Radioactive carbon-14, is made in the atmosphere. The ocean uptakes that carbon. That carbon sits in the ocean for a while, right? Before it eventually precipitates out and can potentially be used to make a shell. So the age of the carbon that's making the calcium carbonate shell, right, which is, that's what I'm going to jump back to because that's the easiest example for my brain to find. That carbon was maybe made a long time ago, right? If that carbon was made a couple hundred years ago, right, which is possible, then it's going to mess up the date. Because again, what you're dating when you use radiocarbon dating is you're dating how long ago that carbon-14 was made, right? And in living animals, right, carbon's made in the air. I breathe it in as carbon dioxide, and now it's in my body, right? Or it's I can breathe it as carbon dioxide, but plants breathe carbon dioxide, not humans. I'm a human person, and I know how photosynthesis and respiration work. Oh my god. Oh, that's how you guys know this is live. If this was edited, I would cut that out and never let anyone ever see it ever, because that was a dumb thing to say that I just said. My bad. So plants are gonna uptake some of that atmospheric carbon using photosynthesis, and then I'm gonna eat a plant, or I'm gonna eat the thing that ate the plant in my turkey sandwich later today. And yeah, then that carbon is in me. And is there a delay of days or weeks, maybe a year, between when that carbon-14 is made in the atmosphere because it's interacting with gamma, high energy ionizing radiation from the sun, between when that happens and when it actually gets into my body via turkey sandwich? Absolutely, right? But it's minuscule, right? And so oh my gosh, maybe we can't carbon date my turkey sandwich or whatever have you to the day or the hour, but we can get it within a year or two, right? And that's really good. Anyway, okay. However, okay, so radioisotope dating. So sorry, there was so much wrong with those 2 sentences. That was 1 sentence. Oh no, I just spent 10 minutes on 1 sentence in this. Radioisotope dating may be used to assist in this process by assigning ages to magnetic reversal boundaries recorded in volcanic rocks. Yes. Cool. Once an age has been assigned to the reversal boundary, this age may be transferred to depths within cores. Oh my gosh. All right, we've got to Google something. Because he's talking about seafloor magnetic reversals. I think that's what he's talking about. And yeah, sorry, you can use radiometric dating to assist with that. I was because volcanic rocks you gotta be careful with, right? Because if it didn't completely melt, because you could get a rock out of a volcano, right, that wasn't completely melted, that just gets shot out, and so that's the timing is wrong. But if we're thinking about at the seafloor, we're having full liquid magma come up, solidify, then that would work. I'm just trying to think is this gonna work? Anyway, okay, let's continue. This was hard. Reading this and reviewing it is hard because you can't do a thing that you normally can with science papers. which is assume you're not being knowingly lied to, right? You can't assume with this that he knows the very basics of the field. But you, turns out, can in regular science papers, right? Oh my goodness. Okay. Ooh. Okay. So once an age has been assigned to the reversal boundaries, again, this is like calibrating or like lining up dates, and like, with seafloor spreading, right? If you just take the rate of seafloor spreading, which you can directly measure with like GPS, so we can directly measure the rate at which seafloor spreads via GPS, and if you take that and you compare that, and so then from that you could extrapolate how long it took for a rock made at the center of the spreading to make it to the end, right where it's subducting under a continental plate. Right, you can guesstimate, if you will, the age of the seafloor, and it turns out that age, I know for like the Atlantic seafloor, I think that's about 250 million years. Please don't cite me or quote me on that, but that's like the number I remember off the top of my head. And that number like matches up, at least roughly, right? Matches up pretty darn close to what you get if you actually date the rocks, right? So there's multiple ways to like date these things. And that's what scientists do. They use multiple methods and make sure that they're all lining up. Multiple independent methods, make sure they're all lining up. And that's a true thing. And that's what this is talking about. So let's use some things we already know about these rocks and use that to kind of help us out and make sure, we're staying, let's put up, it's just like it's bowling, right? You're bowling for small children, right? Or for people who are bad at bowling. Let's put up the gutter rail things, the bumpers. There we go. Let's put up the bumpers and keep you in the lane, right? Because we have these bumpers as a tool. We know other information. We don't have to go into this blind. Anyway, so cool. So we're saying like, oh, hey, we can see a magnetic reversal here. That's what I think he's describing. Like, oh, hey, we know there's a magnetic reversal here because of this data and this data and this data. So we can, we'll apply that date here, blah, blah, blah. So we'll use things that we know to help us. I keep wanting to say correlate, and I mean calibrate. Thank you. There we go. Found it. Calibrate. To help us calibrate these ages and make them more precise. Cool. Love that, right? When we can throw the more independent methods we can throw on dating something, right, the better, because we know when all of those dates agree, right, and they're all they're not all like exactly the exact same year, right? But think of it as like shooting arrows at a target, right? If the right answer is the bullseye, then what we're doing is these arrows are hitting around it, right? So we're kind of circling that bullseye and getting closer and closer and closer. The more independent methods we apply and the better our methodology becomes with time, the better we get at stuff, right? Okay. So the simplest possible age depth model for a seafloor sediment core would assume that the sediments at the location has been deposited at a perfectly constant rate throughout Earth history. Yeah, that would be the list, but we know that's going to be errors because that can't be true, right? It's not going to be a constant. I'm sorry, I just literally hit my mic because I talk with my hands. That's literally not going to be true, but that would be the simplest model, right? Such a model would also ignore the possible complications of compaction of the sediments, absolutely, distribution of the sediments by ocean currents, or disturbance of the sediments by marine or bioturbation. All of that is totally true. However, even uniformitarian scientists, even regular scientists, don't believe that past processes have been that uniform! ! There's absolutely no excuse to ever use an exclamation point in formal writing. Don't do it. Rather, they believe that the sedimentation rates, though slow and gradual, have varied somewhat in the past, with some times characterized by sedimentation rates that are higher than average and some with lower than average. Yeah, man. By the way, this is written like, and it took me, a young Earth creationist, a real scientist, if you will, to point out bioturbation and ocean currents exist. Right? No, that's not what happened. Right? Like regular old scientists, right, know all of these processes and took that into account when possible. Okay. So a technique that can be used to help figure all this stuff out is orbital tuning, to determine the presumed changes of these past rates. Presumed changes, my guy. Again, using that presumed, which is like assumed almost in bad faith, right? Assume without evidence, right? Assume without backup. So we know that there's changes in these past rates, right? These different things happen. So what can we use to help us calibrate our data, right? Because we didn't have measurements of ocean currents a million years ago or even 100 years ago. So what else can we use as a calibration tool, right? That's the question. Okay. Although the orbital tuning method may utilize different mathematical techniques, the conceptual heart of the method is fairly simple. Adjust the timescale for the sediment core so that the wiggles match expectations of Milankovitch's hypothesis. This can be done with a variety of methods. Okay, so what he's saying here, right? What he's saying, right? What he's trying to argue is that there's circular reasoning happening, right? That's going to be the big skeleton in the closet. That's what it's probably going to try to say. Cool. Is that so this is the circular argument that I guess I'm making an assumption, or I'm like making a prediction here. And my prediction is that what he's trying to say is that, look, this is circular reasoning. They use the temperature data to support the Milankovitch hypothesis, but they use the Milankovitch cycles, the orbital processes, to tune the temperature data, right? Of course, that's not what's happening, right? Like we're smarter than that. I do have two. I'm gonna put my hair in pigtails under my hat. Okay. Because today is a day where I don't want my hair to touch my neck even a little bit. All right. Look at that. I would argue that one is never too old for pigtails. Okay. I'm going to maybe try to stop fidgeting with my hair, but who knows. Okay. The tuning process. There we go. Also, this continuous use of wiggles is driving me absolutely insane. That's not appropriate language. Again, this is formal writing. This is formal professional writing. Let's use formal professional language. If I was explaining this like in a classroom setting, you know what I mean? Like if I'm explaining this conceptually, sure, we can use wiggles. But then we'd need to get down to, okay, and then here is the actual precise technical language to describe this, right? And here we're writing a paper. Again, formal writing, formal communication. We should use formal language. So if you're going to say wiggles, it should absolutely be in quotations. So a great example of a term that we use that's used in formal writings, so in scientific papers, in atmospheric science, that's my field, that's what I do, is the term waviness. And that's generally waviness, right? That's generally put in quotations because it doesn't have a formal definition in the literature. It is a term where most atmospheric scientists, we have a sense, we kind of know what it means, but it doesn't have a formal definition. And like when we say waviness, we're usually talking about like the jet stream and talking about the waviness of the jet stream. And we kind of mean a combination of amplitude and wave number. So wave number is so a frequency. Think about a frequency, but like the jet is like a sine wave, and it can have multiple things, but it goes around. We're on a sphere, so things aren't quite as simple. So wave number is kind of how many distinct waves can you count going around a latitude circle. And so if you have, I would say the jet is like a jet with a wave number of 5, of like 5 wiggles, if you will, 5 distinct like peaks and troughs, right? Distinct periods. going around a latitude circle is a wavier jet than a jet with only one, right? It just goes around once. Or if you have a jet with like where the amplitude of its wave is real big, right? So we go like this instead of like this. I would say that this is a wavier jet than this, right? But so that term doesn't really let you compare. Again, there's not a formal definition, and so it doesn't really let you compare. Well, what if I have a low wave number but a big amplitude versus a low amplitude and a high wave number? Which of those is wavier? I don't know. So it's a term we use to get at a general concept. But it's used very like everybody knows we don't know what that everybody knows in my field that doesn't have a specific meaning, right? Like we know what it means, but it doesn't have a formal definition. Unlike other terms like wave number, right? Or amplitude or energy or whatever, like wave energy or whatever have you. But those aren't always the most useful term to communicate the concept. And so again, if we're just communicating a concept, sure, use wiggle. But informal communication, if you're using an informal, undefined term, that should be like in quotations, right? You need to indicate that I'm not using formal language here. Anyway, I'm sorry I am harping so much on this term wiggle, but it's driving me nuts because it feels like he's using informal, undefined, or poorly defined language in this technical field. Obviously, wiggle has a English definition, but I'm talking about a scientific or technical definition because this is technical writing. He's using this informal term, in my opinion, to decrease, not to increase the understanding of his audience, but to decrease his audience's trust in the scientific process being described, right? Meh, it bothers me and I don't like it, if that was unclear. Okay. I guess we'll keep reading for a little bit longer. I've got like a whole 30 minutes before I have to go to a meeting that I don't want to go to. Boo. Yes. Okay. What am I doing? I need to click this button. Okay. So the tuning process distorts this. Yeah, so if we stretch out, yeah, so if we go from, okay, I'm not going to read all his arguments. What he's talking about is, look, if we go from depth versus oxygen ratio, isotope ratio, to age, right, my X scale, my X axis is scaled differently, as it should be, because this is an analog, not a direct measure. Right? You think about it this way, right? If you used we can use for children, right? For sort of average developing human children, you can use their height as an analog for their age, right? Because we know you get taller as you get older, right? And so we can say, oh, okay, here, they're this height, and then they're this height, and then they're this height. Right? And when they were this height, their favorite color was blue. And when they were this height, their favorite color was green. Let's say you've got a height chart and every year you measure your kid's height and you put down what their favorite color and favorite animal is. Right? And so your data points are not going to be evenly spaced, right? Because we don't grow the same amount every year. Right? And so, hey, when we're this height and then this year we grew an inch, and next year we grew 4 inches because they hit puberty, right? If we measure it as like favorite animal versus, or favorite color versus height, right? My X scaling is going to be, whatever it's going to be. But if then we take that and turn height to age, right? That changes the scaling of my x-axis. It doesn't fundamentally change the data, but it does tell us, oh, okay, now we see how their favorite color changed over time instead of over height, and the over time is more useful for us to look at, right? But there was a change in like the step size, right? When I went from height to age, because again, it's not a one-to-one relationship. Okay, so he's mad here that it's not a one-to-one relationship. So we compressed this and stretched this when we went from depth to age. That's going to happen, right? Like that's going to happen. And so if you have a problem with, he has a problem with the concept, not the specific methodology that's used. Okay. Cool. That's where he gets the data. Okay. In the absence of clear evidence for the validity of the Milankovitch hypothesis, citation needing. Hey, tuning is nothing more than circular reasoning. I did a thing. I did a good argument. What if we used radiometric dating? What if we used other things? I don't know, right? Like, what if we used, because you could relate like ice cores, we can use that to calibrate. We can use different methods to calibrate, right? And orbital tuning is maybe one tool in the toolbox, and you should only use it when it's not going to be circular, right? Sure, cool, love it. And even randomly generated signals can be found to agree with the Milankovitch hypothesis. Need to see, what is this, Neiman 1993? Yeah, other scientists, I refuse to say this word anymore. Other scientists have also pointed out the potential dangers in tuning methods. Yeah, potential dangers, and like no tuning method is going to be perfect, right? With the age versus height thing. Hey, we know we did it. We know we measured their height every year, but did we do it every year on the exact same day? Did we do it January 1st every year? Right? What if we did it January 3rd? Well, then if we scale everything to January 1st, there's differences, right? That's what this sounds like he's saying. Okay. I want to look at this Neiman 1993. What is that paper? Oh my gosh, there's so much to read. Why? Neiman 1993. Orbital tuning of paleoclimate records or reassessment. Okay, so let's check our methodology. Are we doing a good job? I don't know, right? But that's a good thing to do, right? Check out how well we're doing. And let's go on. All right. Orbital tuning, circular reasoning. So that's your argument. Cool. This is why a pacemaker paper is so important, because the paper was seen as having confirmed the Milankovitch hypothesis. Paleoclimatologists now feel free to assume the validity of the Milankovitch climate forcing and to use that assumption to date other seafloor sediments via the orbital tuning process. No. Furthermore, the ages assigned to the sediment cores are then used to date still other sediment cores, as well as assign ages to deep ice cores of Antarctica and Greenland. So he's presenting this as a problem, right? But what all he's saying is that we use different independent methods of determining the age of data sets, right? Of sediment cores, of ice cores, of rocks in general, right? If I can like dig out a sediment core, right, and like radiometrically date the age of a non-sedimentary rock next to it, that would give me an age for that point in the core, and I should be able to use that data point moving forward, right? And so we have lots of different ways of dating these different things, and we use all of them together to get at the age, right? The age of things, and we update it. And one of those tools is going to be orbital tuning. Anyway, and it's not this straightforward. One paper came out, everybody's like, great, Milankovitch cycles, love it, perfect, good, right? And then just assumed it to be true from then on. Like, no, right? Even Jakey Poo showed a couple places of like challenges to that theory in the literature, right? Because that's how scientific progress is made. Somebody presents a theory, everybody else tries to rip it apart, right? And if it stands up to that scrutiny, then we move forward, right? It's been demonstrated to be a robust hypothesis. Cool. And also like this one paper, again, so that's not the one paper is not the whole body of work. And like that work being criticized, right, is part of that like fine-tuning process for scientific theories and hypotheses, right? Like, oh, okay, so I like this about it, but have you thought about X, Y, and Z? And maybe the author's like, oh, yes, we did. Here's another paper that's like considering that. Or maybe it's, no, we didn't. That's a good thing to consider. We'll get that out, right? Anyway. All right, I'm getting frustrated with this. Potential problems with inferring climate data from sediments. Okay. Also, as indicated by equation 2, these type of oxygen isotope things, which are thought to serve as a proxy for global ice volume, depend upon temperature. Yep, both temperature and the oxygen isotope value of the surrounding seawater at the time of calcite formation. Cool. Neither of these past variables can be measured in the laboratory. Does anybody have a historical science on their bingo card? If so, check that off right now. Likewise, melting of the ice sheets would influence ocean oxygen 18 values due to the large sizes of the ice sheets and their low oxygen 18 values compared to that of seawater. That is true. Also think about, though, like how the water cycle works. Evaporation and melting, and then it gets mixed in. Okay. But high latitude ice sheet volume also depends on temperature. Sure does. How then does one separate these two effects when interpreting the oxygen 18 data? I'm not sure you do. But anyway, temperature itself is a function of both global climate and local effects. Yes, but this is going to be a function of the oxygen 18 ratios are going to be a function of global climate as opposed to like local effects, right? Because it being warm here one day isn't going to noticeably affect these like global oxygen 18 ratios, right? So these are you can't use these seafloor sediments to measure, like, those aren't a good measure of like local temperature. That's a good measure of global temperature, especially it's like global temperature with local variations, right? Not, oh, hey, it was 70 degrees on this day 2,000 years ago, right? We can't do that, but we can talk about global changes. Cool. How does then one deconvolve which part of the temperature is due to global climate and which is due to local effects? You don't, right? You don't. And so basically it can tell us these sediments, and it is a good idea to take these types of sediment cores from as many different locations as you can, because that, again, all of these are going to start narrowing in on a bullseye. But basically these are not going to be precise enough to tell us about those local effects. So again, it's global temperature with local variations, as opposed to it was 70 degrees this Tuesday 2,000 years ago. Paleoceanographers will often stack data from multiple cores in an attempt to contain an average signal that minimizes locally induced noise in individual cores. Yeah! Hey! I kind of guessed that off the top of my head because I'm not an oceanographer or a paleoclimatologist. Anyway. But this process requires data from multiple cores. Sure does. For instance, although the pacemaker authors combined data from 2 different cores in order to produce a longer composite, their procedure did not reduce possible noise via an averaging process. Carter et al. 2002 have acknowledged that the noise from local effects is a potential problem. Yeah, that's going to be a problem for the data, right? It's going to make your data less precise. But again, data having problems, data not being perfect, doesn't mean it's not good. So if this is a real critique that we're going to spend over 3 pages, or excuse me, 3 separate papers, I need you to be specific, right? Give me numbers, right? And the fact that he's not giving me numbers when he could, because he can cite a paper, right, is upsetting to me. And what's the word? Sus. It's a little sus, right? Be precise. This problem is especially acute for studies using planktonic foraminifera, because those things, you're not going to make me say it again, are free-floating and more likely to be influenced by spatial and temporal variations in temperature. To be honest, you kind of want that, right? I think, because wouldn't that mean that this is it's less of a measurement at this location and more of a global measurement? A good albeit dated overview of the problems confronting attempts to infer past climate from those are found in Word 1984. Also, hey, 1984 was a real long time ago, before I was born. And so like our methods have improved. And this paper is not, this paper is relatively new. Okay. Orbital tuning and circular reasoning is our next section. When was this written? 2016. Yeah. And so like if you're going to levy these real critiques, right? If you're trying to like really levy critiques, you need to be more precise. I don't really want to do this guy's homework for him. Maybe we should briefly check out that Ord 1980 whatever. Table 1. What are all these tables? I don't even know. Okay. Ord. Oh, good. That's from Creation Research Society. No. We're not gonna go over that. No. Okay. We maybe would read this Neiman paper, Orbital Tuning of Paleoclimate Records, a reassessment. So that's just looking at how good are our methods. And I bet their conclusion, I can tell you what their conclusion is. Hey, these are some known problems. These are going to be sources of error in the data, but it's the best we've got right now. If we had better, we'd use it. Anyway, and so if anybody here is saying that like, well, what do you mean? It's the best you've got. If you had better, you'd use it. Doesn't that draw into question all of your current conclusions? Like if we waited for perfect data, we would never progress at any point, right? And climate change is a great example, right? As we have added more and better data, all of that data supports the initial conclusion made with more sparse data. And in fact, it shows that the initial conclusions like weren't, it's worse than we initially thought. That's what the adding of new data means, right? So sometimes, yeah, if you add new data, it undoes, like it sort of negates. And we talked about this with like the what did I talk about? The nemesis hypothesis. At one point in time, we thought we had evidence to support periodic mass extinctions. Not that there have been multiple mass extinctions, but mass extinctions were happening with a specific periodicity every however many years. And turns out with better data that that's not true. Like, oh, okay, cool. So we could move on. I forget my point. Okay, I'm brain dead. I've got a meeting in 12 minutes and I need to go get lunch. So you guys are cool. Thank you so much for hanging out in Journal Club. I hope you're having a beautiful day and you're a great person and you're gorgeous and magnificent. So yeah, okay. Have a great day. I'll talk to you guys later. Bye, team. Andrew.